So my name is Srinivas Reddy, and I'm a product marketing manager for Marc. And in today's webinar, we will look at the importance of contact analysis in simulations and FEA approaches in addressing these problems. Or it could also be between the multiple assemblies. And this interaction could also occur even during, across different regions of the same component. Contact problems that we come across during our daily life. And so whether you work with gears or even machinery components, or seals, stents, or implants in biomedical, simulating contact behavior accurately is very important so that we get the loads and so the stresses and strains accurately in the simulations. So let us see why contact needs special attention in FEA. Finite elements are based on the concept of local support, whereby the elements are aware of only the connected nodes. And the elements that are not connected by a shared node can penetrate as they're not aware of each other. And so the standard method itself needs to be adapted to ensure non-penetration of all the elements and nodes. And with the nonlinear deformations, engineers also need to be concerned about the changing contact zone and pressure because as it changes, the deformation and the loads, they change. And also even the failure of the material. For example, if you have a crack propagating, so your contact zone has changed at that point, and there are some new elements, new nodes that get created, and which also may need to be checked for contact. And also the friction effects affects the stresses and the deformations and near the contact zone. And there could also be some heat generation due to the friction. And multiphysics phenomena like this and other phenomena either due to magnetostatics or Joule heating, and any of these things should also be accounted for in a contact analysis. There are several methods devised to address contact problems using FEA, and these include penalty methods, Lagrange multipliers, augmented Lagrangian, solver constraints, and several others that you see listed over here. And each of them has its own advantages and disadvantages, and in order to obtain good results from the solver, you should understand the parameters that govern the method that is used for contact. And Marc itself it does support several of these methods for various contact scenarios. It does support penalty method and Lagrange multipliers, augmented Lagrangian, and solver constraints as well. And depending on the situation, a different method is used. Nodes and elements form the key components of a finite element mesh, and the contact methods could work either by detecting contact between just the nodes, or contact between nodes to segments, or even segment to segment. And when I say segment, what I mean is it could be edge or a face, edge in the case of 2D or even 1D, and face would be in case of 3D elements. And it could also be a geometric entity. It could be a curve or even a surface, depending whether it's a 2D or a 3D problem. And in a node-to-node approach, for example, a gap element method, contact is detected only between meshed parts. And so the meshes of these parts where the contact is being detected, they should be aligned, the nodes should be aligned so that the contact is detected properly. So you can see that this approach is limited to small deformations, and in the case of large deformations and a large amount of sliding, this method fails. And so in nonlinear analysis, node-to-segment approach has been very popular and used by most nonlinear solvers. And in this approach, contact between a node with a segment is checked. And some of you, when you're talking about the master-slave approach, if you're familiar, so this is the method that is generally used. And since the segment can be either a geometry or an element face or an edge, so this provides a much more general method to address the contact problems. However, the contact detection can be mesh sensitive, although there are some workarounds in some scenarios to address this particular problem. And finally, the segment-to-segment approach is much more general, and since the contact between segments, not just node to segment, but segment to segment is checked, it leads to much more accurate simulations. And although it does require a bit more computational resources, you would get more accurate results. And this method is not mesh sensitive, and so you can also sometimes save just by saving the amount of effort on iterating of the meshes. Historically, contact capabilities of Marc have been leading the industry in terms of ease of use, robustness, and also the power of this capability. And Marc provides node-to-node, node-to-segment, and segment-to-segment capabilities, all three of these capabilities. And as I mentioned earlier, both the node-to-segment and segment-to-segment capabilities are quite general implementations in Marc, such that they are applicable to both small sliding and large sliding problems, and also large deformations as well. And more importantly, Marc reduces the amount of input that the user needs to provide and the amount of effort that the user needs to put in to create these models. And the capabilities themselves are quite general, and you can analyze multiple contact possibilities. This includes solid-to-solid, and shell and beam, or beam to beam, and also it includes the shell edge contact as well. And with the contact, the moment can be transferred to solid elements from both the beams and shell elements as well. So users don't have to worry about creating special multi-point constraints between the shells or beams and the solid elements. And either due to large distortions or failure, a part may need to be remeshed during the analysis. And this means that the mesh boundary also may need to be redefined on the fly. And Marc's contact capabilities work quite well with Marc's automatic remeshing. And the contact state and contact bodies are redefined during the analysis as needed. And the contact capabilities are also extended to support multiple physical phenomena. And you can study heat transfer across the components, and you can perform coupled analysis where heat may be generated either due to plastic deformation or friction, as I mentioned earlier. And in addition, electrostatics, magnetostatics, or electromagnetics, induction heating, and Joule heating are a few other multiphysics phenomena that Marc addresses. And this is where contact features are quite useful in simplifying the modeling effort and also improves the result accuracy. Since Marc uses much more intuitive contact body approach, it is quite easy to set up the contact model. And there are two distinct types of contact bodies defined in Marc, deformable and rigid. And a deformable body is a collection of finite elements. And this is what you see on the slide on the top figure on this slide, where all the contact bodies are deformable, and we have multiple contact bodies. You can see here we have the rod, and we have the block, and we have the bolts, and so on. And the other type of contact body is a rigid body, and in the case of rigid body, where you define using the geometry, it could be curves or surfaces. And as an example, you can see at the bottom, where you see the cylinders are the rigid bodies. These are not finite elements. These are just the geometric entities as come from a CAD file. And there are also like elements. There's also mesh in this tube bending problem that you see here. And another type is if you're interested in temperature distribution within the body, but want to treat it as rigid for structural purposes, you can also create a special type of rigid body where there would be heat transfer across the mesh, but it would still be treated as a rigid body. And Marc also allows you to customize the contact detection. In some cases, like in example at the top here, you could see that bolts themselves may not touch each other. So, and also the friction coefficient and other, like for example, even heat transfer coefficient between different contact pairs would be different, would have different values. And in all these scenarios, you may want to customize. You may want to specify the properties between pairs and also specify how the contact is being checked. So in for these situations, you can use a contact table to customize the properties and the contact detection, and this provides much more flexibility in terms of the contact setup. And finally, the friction plays a key role in development of contact stresses and how the motion, how they slide across each other. And so for that purpose, we do have several friction models to simulate the friction behavior in the simulations. And in the next few slides, I'm going to summarize some of the newer capabilities in Marc and related to contact. And the multiphysics contact capabilities have also been enhanced, but I will not be covering them in this presentation because of the amount of time we have. And so we talked about the segment-to-segment contact approach earlier, and this has been implemented in the past few years. And the advantage of this approach, as I mentioned, is that it does not follow the master-slave approach, and it does not have the mesh dependence problems that node-to-segment approach may have. And so you can expect smoother stress and strain contours with this method. And also this method is available for both linear and quadratic elements. So in this example that you see on the right side, it is a simple one, but nicely demonstrates the differences between the node-to-segment and the segment-to-segment approach. As you can see here, the middle one in the node-to-segment image, the contact is a little bit patchy, whereas it's much more smoother and continuous in the segment-to-segment approach. And here are a couple of other examples that you can see for segment-to-segment approach. And on the left side is the boot model. Sides. And for the as of the next one in the oil industry and machinery and even biomedical industry. Overlap during this and during analysis, as you can guess, could lead to either penetration and even the non-detection of contact. If the penetration is too deep, it may not, the solver may not even detect contact very well. And this means incorrect contact forces and incorrect results overall. So with Marc, you can remove this type of overlap without accumulation of stresses. And so users don't have to spend time cleaning up this geometry, as it is automatically taken care of by the solver. And here is the example, one example here. There's some overlap. As I said, in some cases that is intentional. So that is the second reason. The overlap itself could exist prior to installation. And so, for example, a seal could be created with its original geometry, and with FEA, you may need to figure out the stresses after the installation of the seal, after you stretch it and place it in position. So interfet usage is quite common in machinery components like either spur gears on a shaft and the coupling, even tire mounted on a rim, bushings, valve seats, and any of the rubber seals and so on. And in some cases, the amount of interference itself could be quite high in order to figure out the stresses. So here is one example of the interference that I thought where that's there at the beginning, and the stress-free contact after the interference is removed. So we do have this penetration here. And in this case, we just want to move it up, but we don't want any stress buildup here. So we do have this simpler model just to demonstrate this particular capability here. And you see that the interference is removed and there's no specific stress. It is detecting contact in this region. So you can see by that color change where there is some contact. And as of the second one, which is probably much more common too, like where FEA analysts are much more interested, is the development of stresses once the interference is we also need to figure out the stress buildup in the seal and also the grooved structure. And since the amount of interference here is significant, resolving the interference requires new interference fit capability that is available in Marc. And there is no single approach that could address all types of interference, so several options are made available. With generally a little bit smaller values of interference along the normal direction of the touch surface, and user can control the number of increments or even the time during which the interference fit can be achieved. And the other methods are much more general and allow for larger amounts of overlap between the contact bodies. And in all this, the general scheme is to specify an initial pseudo movement of one of the overlapping bodies such that the overlap gets removed. And after that, once the overlap is removed, it's followed by gradual removal of this movement such that the interference fit is achieved. And the user would have to specify this initial overlap and the pseudo movement of the overlapping body in all these cases, except for the automatic method. And in the case of the automatic method, Marc computes an initial penetration of the contact body, which is then resolved over a load case. So the final one is the tube-in-tube contact. Both tube-in-tube and beam contact behavior are encountered in several engineering applications like either drilling operations or Bowden cables, and even biomedical applications that might require catheter placement. And with Marc's general purpose beam contact capability, which uses the segment-to-segment contact approach, it is very simple to set up any type of contact problems that involve beams. And this includes beam to solids or beam to shells and even other beams that you can, as you can see at the top here. And you can also solve a tube-in-tube contact type of problems where tubes could have arbitrary cross sections. And in the top example, you see that there is contact of a tube, one tube with another, and then there is also another tube inside. And once again, this is being shown in 3D as the shell elements here, but in reality, these are beam elements. So just for display purposes, they're being shown and like this. And the same as here at the bottom one. We would have beam elements with an arbitrary cross section, and once again, beam. There's one tube inside another tube, and we have a square cross section here and so on. And there are other beams at the bottom too. These beams could have arbitrary cross sections, including the circular ones, as you see here, regular solid ones, and the arbitrary solid sections as well, and even thin-walled open sections. And using these beam elements, you can see that you can reduce the model size and also increase the solution speed because you don't have to model everything with solid elements. So here are some examples of the sections that I mentioned about, and you can have practically any type of sections in order to solve these types of problems. So at this point, I'm going to demonstrate a couple of capabilities that I talked about. The first one is the interference fit, and the second one is the tube-in-tube contact problem. And please give me a moment while I share my screen. So first, let me go to the interference fit problem. I do already have the mesh, and we have two tubes. This is, as I said, as a simple 2D problem, and as you can see, it is the outer tube is fixed, and the inner one is right at this point. There are no constraints on this, and there is certain overlap here that you can see all around. And I also have some material properties already specified. The main thing here is, in order to perform the interference fit, is we do need to define the contact bodies. So I'm going to use the automatic detection method. So I have the contact bodies, and Marc uses the default names. So I could, the first one is, you can see that is inner one, using the set that I have already created, and the outer one, so I'm just going to name it outer as well. So we have two contact bodies. And the next thing is we need to create a contact table, because we need interference between just these two contact bodies. I go to contact table, a new one, and over here I can go ahead and use the default contact. Since it is by default, you see it does check contact with everything, even self-contact. I'm going to leave it as it is because it's a small enough problem, although there is no self-contact here. Then we go to I click on one of the buttons, and we need to specify the interference between those two bodies. So I go to that particular contact pair, and I go to interference fit. And we do want interference fit there. And once I select that, you see that a couple of other options came up. And here I can go with the contact normal. As you can see, the interference is along the normal zone. And you could also use, I mentioned some of the other methods, like translation, scaling, and the automatic approach, and even the user subroutine. So you could use any of those, but here I'm going to use the contact normal. At this point, we do need to know the amount of closure, the amount of interference, the maximum amount. In this case, I already know it. I already measured earlier. So it is a 0.06. And notice that we do need to specify a negative sign. I specify the amount of interference. And at the next point, we need to specify some kind of ramping. So because it is when the interference is a little bit significant, it is best to do it in more than one increment. So we do need to specify some kind of ramping. I have that defined. I'm going to select this, but I will show the function ramping table that I have created. So I go ahead and select that. And at this point, we are set with the contact table. And I go ahead and click on OK. Let me go to the contact, the table that I have used there. So you see, this is the ramping function. So initially, there is the amount of interference, which is 0.06. And after at time equals 1, we want all the interference need to be removed. So it is going from 0.06 all the way down to 0. So that's how we defined the ramping function. Let me go back to the model view. And we do have the contact table defined. So at this point, we also have boundary conditions and material properties defined. So I can go ahead with the load case. And we do need to make sure we select the contact table, because that needs to be selected here. And I can go ahead with the automatic adaptive time stepping scheme. And we could also specify a fixed number of increments. And we do have a load case, and the same thing with the jobs. So let me select the load case we have created, and I'm going to go ahead and select that initial contact table as well. And with the analysis options, since it could be a large strain problem, I go ahead and select that, and if needed, yeah, we can go ahead and select some stress results and so on, and click on OK. And this is it. Like, so we have the complete model at this point. So the main point is, as you can see, like, in difference is as you create the contact. When you create the contact table, you just need to specify the amount of interference in this particular problem. So I already have the results file, so I ran this earlier. So again, it doesn't really take much time. It takes just a few seconds. So if we look at, so you see that slowly it resolves the interference. And as it is animating, you might have noticed it seems to be rotating slightly, and that is something you should expect, because I did not really put any constraints on the interior one. So that's the reason it seems to be moving a little bit. But at the end, so it did resolve the amount of interference. If you do want to avoid any kind of rotations, you can place some kind of constraint so that it doesn't actually rotate in this case. So that is one example. And let me go ahead with the other example as well. And so this is a beam model. And as I mentioned earlier, we do use beam elements for tube-in-tube contact. So we have actually as you can imagine, it is a little bit harder to visualize the beams. So you do see that there are two sets of beam elements. One is inner, so we have a solid section, and there is an outer sleeve. So that is up to about this point here. And the thing is, yeah, we do have the material properties here, and as of the boundary conditions, we do have fixed boundary condition, and I'm applying a load on the other end. So let me show that as well. So we have the load being applied on this side. So we have the material properties defined. Once again, the main point of interest here is contact. So let me go ahead and set up contact. Once again, I'm going to use the detect meshed bodies, so it makes it much easier to create these. So once again, this also, there's the inner solid beam elements, and then we do have outer, that is actually some kind of a sleeve. So we have those elements as well. So we have two contact bodies at this point. There is one more thing that is important. As you can see, like for beam elements, we do need to specify the cross-section properties and so on. So we do also need to go to the geometric properties. And so let me create the geometric properties. The first one is the solid section beam. So I'd go in there, and this is, let me add the elements. And we do need, I have already created the set. So this is for the inner one, that is the set. And we do need to specify the properties. And this has a property of about 0.25. So that's the diameter of this one. And so that's the only property that we need here. And you can, if you specify any others other than the circular, you can go ahead and, if you need, you can use any of the other cross sections here, or you can even use the beam sections, where you can over here you can use beam sections and create any arbitrary cross section as well. So we have one beam cross section defined. We have the other beam. So that one is a thin-walled beam. So that is a sleeve, that is not a solid beam. Once again, I go and select the elements. So I have a set defined. So I'm going to select those elements and come to properties. This is also a circular cross section. So, but with the radius of 0.15, and the wall thickness is 0.03. So we have that, and we have all these properties defined at this point. And we come to load case, and we create. In this case, we're not really using a contact table. I'm letting default contact in, which means like contact is detected across any of the bodies, including self-contact. I didn't worry about turning off self-contact once again because this is a small enough model. And we have all the loads selected already. So then going on to jobs, and make sure this load case is selected, and analysis options, go ahead and select the large strain. And in job results, there is one option that I would like, one moment here. I think I may have missed something over here. So we do need, when we select the contact, let me go ahead and create the contact table as well. So we do have analysis options. Let me contact control, and I need to make sure this one segment to segment. And so the other options, we do have either the finer sliding is on, and I don't need friction here. I'm not using friction. And you can use either finer sliding or large sliding, and you can go to advanced contact. And over here, I mentioned about the penalty factors and the augmented Lagrangian options. So if we need, we can turn on the augmented Lagrangian. But in this case scenario, I'm not going to do that. So once we have the segment-to-segment option turned on, so this was one thing. So it was the segment-to-segment option that I forgot earlier to turn on. So this particular button comes active, and so here you see an option called expanded beam post file, and this is what actually creates that solid looking like beam elements. So it actually creates, so they're not fully solids, but actually the boundary elements that just for visualization purposes, it creates some mesh on the boundary. And so that is what is needed for better visualization. So I go ahead and select that and click on OK. And once again, I have already run this model. So let me go ahead and open in the results file. And you see, like, once at this point, you still see the stick model, right? Like you see either one set of beam elements, the other set of beam elements. And so let me go to open. And you see that model and beam. So open that results file, and that contains this mesh. So when I selected that beam post file, additional beam post file, so that is what created a second results file, so that you can see the actual beam, the beam cross sections. And if you have a different cross section, you're going to see a different cross section here. So here, in this case, it is circular, so you're just seeing the circular shape. And you can go ahead and see the entire deformation over here. So with that, so that concludes my demo part, and let me go back to the presentation to conclude the presentation. And so to quickly summarize, we did what we had covered in this presentation. We reviewed the various contact methods available and some of the newer capabilities with methodology that provides robust and accurate solutions. And we have multiple materials and so on. So thank you very much for your attention.